Making Sense of QFT. Lecture 9. Darwin-Breit Electrodynamics by Eugene Stefanovich. Originally, I planned to fit the whole course about QFT into 8 lectures. I have mentioned briefly the Darwin-Breit electrodynamics in the 7th lecture and thought that this would be enough. But then I changed my mind. I think that this topic is so important that it warrants a full separate lecture. Unfortunately, Maxwell theory is still regarded by many as the only possible theory of electromagnetic phenomena. But in this lecture, I'm going to describe an alternative approach, which offers many advantages. Darwin-Breit electrodynamics describes successfully many electromagnetic phenomena. You can read about these phenomena and their explanations in the 3rd volume of my book, which also has many references. Here I would like to focus just on one specific example, which is the Aharonov-Bohm effect. I will show how one can approach this effect from the standpoint of Darwin-Breit theory. I will start from the Hamiltonian describing interaction of 2-point charges. Then I will derive the Hamiltonian for a charge in the field of a current loop. And then we'll see what happens when many current loops are assembled in an infinite solenoid. We will solve the quantum mechanical problem for a wave packet moving in the field of such a solenoid. And we will see that the center of the wave packet moves uniformly. This agrees with Maxwell theory prediction that there is no magnetic field outside an infinite solenoid. Our calculations will show that the total phase of the wave packet is affected by the solenoid's potential. And this will be our explanation of the Aharonov-Bohm effect. At the end, I'll formulate a few conclusions. In 1959, Aharonov and Bohm predicted a very interesting electromagnetic effect that now bears their names. Suppose that we erected a thin but infinitely long solenoid along the z-axis. A steady current flows through the coils, so the solenoid has a constant linear magnetization density μ2. Now suppose that we begin to shoot electrons. They can go around the solenoid either on the right, the red path, or on the left, the blue path. Then we will measure the interference picture created by the electrons behind the solenoid. The interesting point is that Maxwell theory insists that there is no magnetic field in the space around the solenoid. All field is concentrated inside the solenoid tube. Therefore, one could expect that the interference picture would not be affected by magnetization. However, Aharonov and Bohm predicted that the interference fringes will shift depending on μ2. They calculated the magnitude of the shift, and this calculation agreed exactly with actual measurements performed many years later. Let me stress these points again. Electric and magnetic fields outside the infinite solenoid are zero. According to Maxwell theory, electromagnetic potentials may be non-zero, but the usual assumption was that this should not have any observable consequences because electromagnetic potentials were regarded as purely formal mathematical quantities. The true importance of the Aharonov-Bohm prediction was the experimental demonstration of the physical significance of electromagnetic potentials. This is how the authors describe this conclusion in their original paper. In a theory involving only local interactions, the potentials must, in certain cases, be considered as physically effective even when there are no fields acting on the charged particles. Now, let's turn to the Darwin-Breit electrodynamics, which we derived in lecture 7 as a low-energy classical approximation to the dressed particle QED. In this theory, there are no electromagnetic fields and no potentials. Charges interact by instantaneous action at a distance, forces that depend on particle positions and velocities. Here is an example of the interaction potential between electron and a proton. We have derived this formula in lecture 7. We also mentioned there that this theory can explain all low-energy electromagnetic phenomena. It is also possible to take into account radiation effects, but for that one has to invoke higher perturbation orders. But how about the Aharonov-Bohm effect? How the Darwin-Breit Hamiltonian explains these observations? This will be the topic of our lecture today. To answer these questions, we have to derive the Hamiltonian of the system charge plus infinite solenoid with current. As a starting point, we'll take the interaction potential between two charged particles presented on the previous slide. To simplify calculations, let's introduce few approximations. First, we will ignore spin-dependent and contact terms. We also ignore Coulomb interaction between the solenoid and our particle because the solenoid is assumed to be neutral. We will also ignore kinetic energy of electrons in the wire. Their motion will be regarded as given. We don't have to pay attention to the fast random thermal motion of wire electrons, because these velocities average to zero. But in our Hamiltonian, these velocities enter in a linear fashion. So the thermal effects average to zero, and we can assume that all conduction electrons have the same drift velocity v2, which is determined by the wire current. If we apply all these considerations, then it's not difficult to obtain the interaction energy between our charge, labeled by index 1, and wire segment dl, labeled by index 2. Here, ρ2 is the linear charge density of conduction electrons. v2 is their drift velocity. In the next step, we assume that the wire is arranged in a circular loop with radius a. Then we have to integrate the above interaction along the length of the loop. This can be done without difficulty. This is the resulting expression where vector mu2 is the magnetic moment of the current loop obtained by the standard formula. Our goal is to derive interaction between a charge and an infinite solenoid. Such a solenoid can be well approximated by many current loops stacked on top of each other. Therefore, we have to integrate the charge loop interaction over the infinite length of the solenoid. This integral is shown in equation 6.37. As you can see, the interaction potential V long decreases as the inverse second power of the shortest distance between the charge and the solenoid. Once we define the interaction potential, we have everything we need to solve equations of motion. As a reminder, here is our full Hamiltonian. The first term is the classical charge's kinetic energy. The second term is relativistic correction to the kinetic energy. And the third term is the potential energy of the interaction between the charge and the solenoid. By the first Hamilton equation of motion, we derive the time derivative of the charge's momentum. The second Hamilton's equations of motion gives the time derivative of position or velocity. Finally, we differentiate by time the last equation and obtain acceleration, which after routine calculations turns out to be equal to 0. So we obtained a curious example of a non-trivial potential in which charges move without acceleration. This is our version of the well-known fact that the magnetic field outside infinite solenoid vanishes. But if acceleration is 0, then dynamics of particles should not be affected by magnetization. Then what is the explanation of the Aharonov-Bohm experiment? We have to keep in mind that we are dealing with quantum particles here, which are not the same as classical material points. They are better described by wave packets. Here I showed an example of such a wave packet. It is described basically by 3 parameters that depend on time, as the packet moves in space. First, the center of the wave packet is characterized by its position r0. Second, the packet has a definite momentum p0, which is inversely proportional to the wavelength of the oscillating wave function. Finally, there is also a purely quantum parameter phi, which is the average phase of the wave packet. Using these 3 parameters, each wave packet can be approximately represented in the form given by equations 6.108 and 6.109. Next, we substitute this ansatz in the Schrödinger equation. And obtain a set of 3 equations for our parameters. In the first one, we recognize the first Hamilton's equation of motion expressing the time derivative of momentum. The second equation is for the time derivative of position, and it is the second Hamilton's equation. These results confirm that the center of the wave packet moves according to the laws of classical mechanics. In the case of a charge interacting with solenoid, this means that the charge moves uniformly along straight lines, as expected. Let us now take a look at the third parameter, the phase. Its equation has a solution in the form of the so-called action integral, where we are supposed to integrate kinetic energy minus potential energy along the classical trajectory of the particle. The presence of the potential energy here implies that, unlike momentum and position, the phase of the wave packet is affected by the magnetization. This gives us the opportunity to explain the Aharonov-Bohm effect. Recall that we are looking at charges that can move near the solenoid along two straight trajectories. The charges are represented by wave packets, and we will assume that both left and right charges start their motion as wave packets of the same form. While traveling along the two trajectories, right red and left blue, the wave packets would accumulate different phases because the values of the potential are different along these two trajectories. This means that at the end of their journey, the two wave packets will get different phases. So the result of their interference will depend on the magnetization of the solenoid. For the shape of the interference picture, only the phase difference is important. Therefore, in the action integral, we can omit the kinetic energy contribution because it is the same for the two paths. Here are some details on how this integral is calculated. As we said already, the motion is uniform, so the position vector is a linear function of time. The only difference is in the x component, which is minus r for the left path and plus r for the right path, where r is the impact parameter. Velocity is constant and the same for the two paths. Magnetization vector is also constant. Substituting all these ingredients into the phase integral formula and assuming for simplicity that the time of travel is infinite, we obtain the accumulated phases. We obtain that accumulated phases differ by sign in the two cases. These formulas are written for the case when we are dealing with electron whose charge is minus e. In other words, the total phase difference is given by formula 7.9. This result is independent on the impact parameter. It is independent on the electron's velocity or energy, and it is directly proportional to the solenoid's magnetization. All these properties agree with the original prediction made by Aharonov and Bohm and with experimental results. So Darwin-Breit theory has confirmed its usability once again. Conclusions. Darwin-Breit theory is a fully relativistic Hamiltonian approach to electrodynamics. There are no fields in this theory. It may be obtained as a straightforward classical approximation to the dressed particle quantum electrodynamics. In this theory, charged particles interact by instantaneous forces at a distance. And the forces depend not only on charge positions, but also on their velocities. Today we applied the Darwin-Breit theory to the Aharonov-Bohm effect. We found that the nature of this effect is fully quantum. In the configuration solenoid plus charge, the charge's acceleration is zero, but the wave packet's phase is affected by the interaction in a non-trivial way. Results of Darwin-Breit calculations agree well with experiments. Thank you.